Hello, AP Psychology students. In the previous lesson, we learned about the old brain structures and the midbrain structures. Today, we're going to be looking at what's called the new brain, and this refers to the folded area that sits atop of the brainstem region and the thalamus and the midbrain region. The other term for the cerebral cortex is cerebrum, which means cap. So we're going to start by, again, I would suggest that you get out your diagram packet, and we're going to start by just labeling the important structures of the cerebrum. Broca's area is in the frontal lobe, and I guess I'll mention the lobes first. The frontal lobe is this blue area, and it is quite large in humans. The parietal lobe is right behind the frontal lobe. The very back of your head is the occipital lobe. And then behind your temples and kind of behind the ears is what's called the temporal lobe. Now, the Broca's area is in the frontal lobe. I will explain the function of that in a little bit. The motor cortex is, you can see a faint line here. It is a strip of neurons that is in the very back part of the frontal lobe, so right about the middle of the top of your head. The parietal lobe is kind of the top of your head, top back of your head, and then the occipital lobe is the back of your head, as I mentioned. But in the parietal lobe, you have the somatosensory cortex, so that is right behind the motor cortex, and they interact with each other quite a bit. And again, I'll talk about that later. Within the parietal lobe is a structure here called the angular gyrus. I'll talk about that as well. And then in the temporal lobe is another structure called Wernicke's area. Broca's, angular gyrus, and Wernicke's are all important for speech and language. Let's talk about the structures of the frontal lobe first of all. This strip here represents the motor cortex. That's the very back part of what we call the frontal lobe. Now, there is no anatomical distinction between this motor cortex and the strip behind it, which is called the sensory cortex. We only know about these differences through scans like fMRIs. At any rate, what we do know a lot about the brain is a lot of what we know comes from when people have a stroke or tumor or brain damage of some kind. So judgment and decision making is a function of the frontal lobe. When people have a injury to that part of the brain, the thing that tends to be affected is their judgment. This is also thought to be the seat of our personality. So in particular, people who have strokes or a tumor in this part of the brain might exhibit really profound changes in their personality. This is what we saw in the story of Phineas Gage that I had you guys watch earlier. The prefrontal cortex is a region right at the very front of the frontal lobe, right behind your forehead. The prefrontal cortex is thought to be the seat of our morality. What's interesting is that moral decision-making, one would expect that people in prison are not so good at that. And as it turns out, in functional MRIs, it appears that they have a less developed prefrontal cortex. Now, we don't know if that's a cause or an effect. We can't really make that determination, but we can make the observation that the prefrontal cortex does seem to be less developed in people who are in prison. I already mentioned the motor cortex that is at the back of the frontal lobe, and this controls our voluntary muscles. So you can see things like our toes, our ankle, and our knee. Our knee is right at the very top and center of our brain. And so we have our right knee is controlled by the left side of the brain, and our left knee is controlled by the right side of the brain. If you were to have a tumor, for example, right at the top of your head in the area of the frontal lobe of the motor cortex, maybe you'll start to not be able to control your knee very well. I actually knew someone that had this happen. He was just a young child. He had it removed, and he has very little evident damage from that tumor because he was young enough that he was able to recover from it. Now, Broca's area, this is an area, so if the mouth is right about here on the frontal lobe, Broca's area is right in front of where the mouth is. Broca's area is on the left side of the brain only, and it is critical for speech production. In fact, if you have a tumor in the region of the Broca's area, or if you have a stroke in the region of the Broca's area, you will have a difficult time being able to produce speech or language, regardless of whether it's in written or spoken form. This was discovered by a man named Paul Broca, who had a patient that had a stroke, and after the stroke, he was unable to communicate his thoughts. Even though it was clear that he understood language, he was unable to communicate with language. When Paul Broca did an autopsy on him after he passed away, he found this part of the brain, and has since been confirmed to be a really important area for speech production. Damage to the frontal lobe overall is going to cause a change in personality, in impulsivity. I know someone who has had a traumatic brain injury in the frontal lobe of his brain, and the result is impulsivity. And so if you know someone that has damage to part of the brain, it's going to be important to try to be supportive, although it can be really difficult, especially if it's a stroke or if it's a brain injury of some kind. It's possible that they can recover, but they might end up actually being somewhat different than they were before the damage. Now, this guy here is a really cute guy, right? He's got like giant hands and giant lips. And you know, for people in class, I have an activity that illustrates, you know, what he represents. But what he actually represents is the somatosensory cortex of the parietal lobe and how many neurons are dedicated to each of these areas in the body. So you can see our hands and our lips have a whole bunch of sensory neurons that are associated with those areas of the body. And the reason why is we use our hands so much, and we have to be able to touch and feel things with our hands. We also have to have and be sensitive to what's going on our lips. If food is too hot, or you know, we need to adjust what we're doing with our lips, and we also speak from our lips. So part of speaking is being able to feel our lips. You might notice after you've gone to the dentist and you've had Novocaine, you can't feel your lips or your tongue for that matter. You kind of talk slurred. That's because not only is it hard to move them, but touching, the touch is important for speaking. So the parietal lobe, like I mentioned, is right about halfway back from the top of your head and about the width of your hands across the top of your head. It is responsible for sensation and perception. It also contains, and by the way, please pause to catch up with these notes, but right about the middle of the top of your head, right behind the motor cortex, is the sensory cortex. So if you look at this, you can see that the tongue and the mouth, they're down, you know, closer to this part of the, you know, just right inside of your skull. It's on the superficial area. Your mouth, your hands are, you know, right about here. And again, where you're going to feel your hip is right, and your knee is kind of right at the top of your head. And this, again, represents the relative number of sensory neurons devoted to each part of the body. So your skin senses, there are receptors right under the surface layer of your skin that can sense pain, pressure, and temperature. And those messages will then go to the sensory cortex. Also in the parietal lobe is the angular gyrus, and you can see that on the diagram in your packet. This is going to transform visual words into auditory code. So the fact that I can read that right now transforms visual words into auditory code depends on all three of my language areas working well, but in particular, it depends on the angular gyrus being able to do that. So my skin senses are telling me that it's cold right now on my arms, and so I'm actually putting my sweater on, and that's because my somatosensory cortex is saying, it's a little bit cold. Okay, the other important function of the parietal lobe is visual spatial processing and mapping. We actually have a map of our world, and if we close our eyes and we think about how we're going to, you know, walk around the block or walk from one end of the school to the other, we've created a visual spatial map in our brain to do that, and that is going to be in the parietal lobe. So people, again, who have a tumor in that part of the brain might have difficulty with cognitive mapping or visual spatial processing. Damage causes something called visual neglect. Now, this is something I describe in my class. It's kind of difficult for me to do it here on the computer, but if someone were to draw a daisy, for example, so follow my cursor. If you don't have a problem with your parietal lobe, you'll have a complete daisy. Okay, you'll have the stem and you'll have the leaves. But let's say that I have a problem with my right visual cortex, or my right parietal lobe, rather. I am going to draw the stem, and I am going to end up neglecting the left side. And so for me, this is the left side. And I'm going to end up drawing just half of the daisy because I am neglecting that part of my visual spatial mapping. It's a really interesting phenomenon. So when we look at the motor and sensory cortex together, we're going to see that they constantly communicate with each other. So if I put my hand on a hot stove, my sensory neurons for my hand are going to feel the heat, and that's going to initiate the motor neurons to pull my hand away. The occipital lobe, this is the part of the brain that contains the primary visual cortex. So running from our eyes, from each eye, we actually have the optic nerve. The optic nerve will go through something called the optic chiasm, and we'll talk more about that in another unit. But this is where the right visual field and the left visual field for each eye will separate. The neurons will. They'll go through the thalamus. We already talked about that. And then they'll end up at the back of your head. And so your right visual field will go to the left side of your head, and your left visual field will go to the right side of your brain. The occipital lobe allows us to interpret color, orientation, and motion. It's really a fantastic system. Our visual system is absolutely amazing, and I will talk more about that in another unit. But it is a very critical part of our brain for understanding movement, how something is oriented in space. And of course, color comes from both the eyes and from the brain. Damage to this part of the brain can cause hallucinations. Perhaps you have fallen back on the back of your head and you've seen stars. That is because your brain neurons have been kind of pressured into making an action potential, and so you see these stars. You can also be brain blind. This means that perhaps your right or your left visual field is you're not able to see because your brain has been damaged in that area. Your eye will work fine, your pupils will work fine, but your brain is not able to take in that information. Synesthesia refers to a confusion of the senses. I have had a number of students over the years that have described synesthesia and their experience with it, and sometimes they didn't even realize that they had it until they were in this class. So they might see a letter as a particular color or a number as a particular color. I actually learned that one of my sons has synesthesia when he was playing the guitar, and he said to my other son, "Wow, isn't it really interesting the way that you see colored lines when you play music?" Well, what causes this? And my other son, by the way, said, "I don't see colored lines. What are you talking about?" So the reason for this is there has been some kind of crosswiring in the brain. Most likely in my son, there is some crosswiring between the occipital lobe and the temporal lobe where the sound is heard. And so for some reason, in particular, when he plays the guitar, which is hearing that is the function of the temporal lobe, he sees colors. Now, this doesn't generally cause people any serious problems. In fact, many people find it to be helpful because, if they see an 8 as a purple, they see purple, they see 8, they know what it is. So it is really not a problem for most people if they have that. The temporal lobe is right behind your temples. So you can see your ear here, and this is your ear canal. We'll talk about the inner ear in another lesson. So the temporal lobe actually sits above the ear canal, and the auditory cortex is above that. So this is the auditory nerve here. Again, we're going to talk about that in another unit. But you do need to know that the auditory cortex is in the temporal lobe. The auditory cortex is actually where sound is first interpreted. Now, on the left side of the brain only is an area near the auditory cortex called the Wernicke's area. Said like a V because it's a German man, Wernicke, who discovered this area. And it is a complement to Broca's area. So Broca's area is important for speech production. Wernicke's area is important for speech and language comprehension. So as you can imagine, if you had damage to the Wernicke's area, when people talk to you, it really doesn't make sense. You're not going to be able to produce speech as very well, even if your Broca's area is not damaged, however, because if your Wernicke's area is impacted, you're having a hard time comprehending language. It's going to be hard to respond to language. There are many substructures of the temporal lobe, and too many for us to really go into in this course. It's kind of beyond the scope of this course, but the temporal lobe seems to be tremendously important for many kinds of emotions and recognition and things that we don't even know yet. We do know that there is a condition called temporal lobe epilepsy, however, that causes one to have what we call a religious aura. I have a video in class from that's called Secrets of the Mind, and I think I will post that video on our Schoology page. In it, there's a man who has temporal lobe epilepsy, and what epilepsy is an overfiring of neurons in the brain. When he has temporal lobe epilepsy, he actually interprets it as a highly religious experience. He feels like he's at one with the universe. Now, this doesn't invalidate any kind of authentic religious experience that one might have, but it is an interesting feature of the temporal lobe that when one has epilepsy there, that they do have this intense religious aura. The association areas occur throughout the cerebral cortex, and they are the seat of numerous higher mental functions, learning, thinking, memory. The brain really is very well connected, and in fact, none of the cerebral cortex is really anatomically distinct. There are some specific areas that we can note, some vesicles and things like that, that we can notice on the brain, but overall, you're going to have all of these areas of the cerebral cortex communicating with each other very rapidly, and that's what makes us such efficient thinkers and efficient at learning. So what I'd like you to do now for your assignment is to think about this picture here and to describe 5 brain structures that are particularly active. Describe 5 brain structures that are particularly active while this woman is painting. So keep in mind, she's going to be moving the brush onto the palette. She's looking at the scenery. She's going to feel pressure. So think about ones that are particularly active and why. And then also 3 neurotransmitters that will be at work in this particular situation. Thank you for your attention. I know I went through this very rapidly, but we do need to move pretty rapidly through this unit. Thank you. Goodbye.